this is UAP detection and analysis. I wanted to focus on multimodal detection. So I have, let me see, 14 different kinds listed: active radar, which is traditional radar; passive radar; microwave band detection, which is similar to what the RB47 incident showed, right? Which is what led to the Alzaphon model; X-ray, gamma ray spectroscopy; proton magnometer, which is one that I've been excited about for a long time. Then you've got traditional optical, right? That's photos and video; forward-looking infrared or FLIR. You have ultraviolet optical photography. Then you've got the Faraday rings that Jared was just talking about. He sent me a couple photos for that. I'll show those. Gravitational lensing, that's Chad Wanless stuff. Then you've got Geiger counter and or scintillator or cosmic watch. Portable neutrino detector, that is something that is really new and very kind of speculative. Then you have audio detection and sonar, right? And the sonar is obviously underwater. So the idea behind this was, why do we want to use multimodal detection? And by multimodal, I mean you're going to have a camera, but you're also going to try and pick up other stuff, right? We saw that in the Nimitz sightings, where they were able to get radar data and overlap that with infrared, the FLIR, and then they were able to overlap that with optical visible video, right? And so when you combine all of those, you get a data set that is more reliable than any single one alone. They kind of multiply each other, and there are several different reasons for that. But I made, again, kind of a list here. So this multimodal data detection is going to hopefully let you determine the size, speed, and flight direction of your UAP, right? It'll also help you determine whether that UAP is a solid physical object. And I think that's really important because people have taken photos in the past of lenticular clouds. Okay, well, it looks like a solid physical object, but it's just a cloud, right? So another thing, if you're analyzing, especially stuff like microwave frequencies and things like that, this may let you identify NHI technosignatures. And this could be a number of different things. Maybe you're picking up like nuclear signatures of some kind. Maybe you're picking up strange EM signatures that you know don't come from an aircraft. There are a bunch of different things that we could basically add into our data set to say, hey, look, here's some video of this object, and I picked up this other stuff, and there's no way that comes from an aircraft, you know? So we've got that. Another thing is detecting and analyzing electromagnetic signatures for communications or propulsion. Again, the Alzaphon model came out of what is believed to be propulsion electromagnetic signatures. So if we're able to capture as much data as possible, maybe we'll get a better idea how these things fly, and maybe we'll pick up some communications between them as well. Another thing, especially stuff like infrared, may let us detect the temperature of the craft as well as temperature changes from things like air resistance. Now, one of the 5 observables, I believe, is that these things fly without air resistance, and the same would apply to USOs. They pass through water, apparently without water resistance. But the idea is, if we can map temperature to different parts of the UAP hull, then maybe we'll see more about what's going on there. Another thing with multimodal detection is red and blue shifting, or gravitational lensing. This comes out of Chad Wanless photos, and I have those later in this presentation. The idea being, if you're taking photos and video, you may see distortion. That distortion could be an artifact of the camera you're using. That does happen frequently. It may also be something that is related to gravitational lensing. And if we can map that down and calculate it, then maybe we could tell more about the drive systems these things are using. I mean, again, Jack Sarfati has talked about the lower power warp drive. Things along those lines may lead a signature, right? They may have a signature that we can use to understand exactly how it's working. Another thing we can use multimodal detection for is detecting stealthy objects that are masked in one spectrum. There is this idea out there that UAP may or may not be able to become invisible. Okay, maybe they're not invisible in all of the spectrum. And so if we can't see it in optical, maybe we can see it in IR, maybe we can see it in UV, maybe we see it on radar, right? Again, having more of those modes available to us reinforces what we're seeing, and it may also tell us other things. For instance, if you see something wink out and it disappears but it's still on radar, then you may have an idea that they're using some kind of stealth. So again, these signatures reinforce the credibility of any one, especially in this day and age, right? Because AI makes it really easy to fake photos and video. And it also lets us rule out stuff like aircraft, clouds, mirages, all sorts of things like that. So I'm going to skip through here. So why use multimodal? Photos have always been able to be faked. Jared mentioned like potential hubcap a few moments ago. Okay, people have been throwing hubcaps and taking photos of those for decades, right? AI software makes hoaxes even easier, you know? Um, even if we're not sure if it's a hoax or not, photos and video only capture a small amount of data. And that's one of the problems with UFO photos is we're going through these digital photos pixel by pixel saying, is this JPEG distortion, right? Or is this something else? We only have a little bit to work with. So the more data across more spectrum we're able to capture, the more depth of analysis we're able to do. Um, Traditional photos don't provide detailed insights to understand what kind of propulsion mechanisms might be going on. They also provide easy fodder to skeptics. I mean, for as many people are uploading UFO photos out there, we also have just as many skeptics out there picking them apart, right? And unfortunately, like when you upload a photo, it's going to pick up stuff like JPEG compression artifacts, even if it didn't have a lot to begin with, because every time you upload those, they get squished a little bit more. So instead of giving the skeptics more fodder and getting into this he said, she said cycle, right, where someone says, oh, it's real, and then the skeptics say no, and here's 20 different reasons why it's not. We want to try and capture more data to be able to say, here's what we got, um, so again, a single data source increases the potential for error, and photos and video are susceptible to zoom and blur issues. So I just ran through some of these. I don't even know if I should go through them, but active radar is the gold standard for airborne object detection and tracking. That is what the military and airports use, right? Doppler radar is more accurate than ever. So radar is getting better. It's being used for weather patterns and things like that now. Um, One of the things that I wanted to highlight, most military and airport radar systems use filters to eliminate noise. So that could be small objects and ground clutter, right? This is something that kind of came to light during that balloon gate scandal where we had these Chinese weather balloons. Well, how come these things weren't showing up? How come it was a giant national security issue? It was because apparently, at least some of them had been filtered out on the radar. The radar is looking for aircraft. It's worried about aircraft penetrating our defenses. It's not looking for a balloon. Okay, well, if that's the case, maybe it's also not looking for UAP. So I have a couple of photos. This goes with the radar part. 1952 Washington D.C. UFO sightings. Saucers over D.C. This was tracked on radar, and at the time, they blamed this on temperature inversions. They said that basically those were causing the bounce back on the waves that was causing false signatures. So again, any one source of these data points can be in error. So that was saucers over DC. More recently, we've got the 2019 UAP swarm encounter. So Jeremy Corbell actually leaked some video of this, and it is radar. It's UAP showing up on radar. So as you can see, we've got like 75 something years of this, So radar is there. Passive radar, I do not have any photos for this. I will try and find some. This is what Mitch Randall has been working on. There's a fellow named David Hooper, I believe, also. And the idea is with a regular radar system, it sends out a beam and measures the response time, right? So I hit something with a beam, and then I'm going to measure the bounce back time for it. With passive radar, you're using a separate beam, and there are some big advantages to that. So you can do with FM or radio transmissions, right? But Starlink and DirecTV have made this more reliable. And basically, what you do is instead of having to go through all the regulatory hurdles and everything, right? Because you can't just blast radar beams out there. You can use beams that are already in place. You measure the beam, you measure the signal response time. It is not quite as good as active radar, but again, Starlink, DirecTV make it better than it was in the past. Um, Microwave band signal detection. This is kind of broad spectrum. I was thinking of the RB-47 incident. That was an Eland aircraft that recorded what are believed to be frequency emissions from a UFO. This is what led to Alzafon getting into dynamic nuclear polarization. So if we can pick up any kind of electromagnetic package from these craft, it could tell us more about what's going on. Another one, X-ray and gamma ray spectroscopy. This was used by UAPX, sort of, kind of, during a field investigation of UAP at Catalina Island. It's also used in astronomy. So, we're looking for very high energy X-rays or gamma rays. And that could tell us a lot about what's going on with these craft. The other one, Proton Magnometer. Again, I don't have a photo. I haven't completely finished this thing yet. Um, it's a proton precession magnetometer, uses the principle of the Earth's field nuclear magnetic resonance to measure small variations in the field. And so it allows you to detect ferrous objects on land and at sea. And so in many ways, from what I've read, because I'm not an expert in this, they are very, very, very sensitive. I've heard that you could see someone flipping a coin a mile away with one of these things. The downside is this is not a detailed imaging device, right? And I believe it is focused on ferrous objects, so it may miss other types of materials. So this is just something to add to our toolkit, you know? So I wanted to go through optical visible spectrum. This part isn't really done, but what I wanted to try and do was showcase we know how this works. Someone sees a UFO with their eyes, right? And then they reach for a camera or a smartphone. So I think one of the important things to point out here is that the quality of this video is improving dramatically over time. Smartphones are transitioning right now from 12 megapixels, which is what your selfie cam does, to 48 megapixels, which is what the raw version of the new iPhone camera does. And I believe Samsung has one too. So our image quality is about to get 4 times sharper for all of these. Another thing that we're seeing is an improvement in file types. It's going from JPEG, which has inherent compression, to file types like HEIF. And so you get a higher, basically a much larger color palette. So you get more detail for stuff like red shifting, blue shifting, and you get less file compression. So you're going to have cleaner images. So we want to try and use as good as we can in terms of photos and video, and that's getting better, every year. The other one is FLIR, forward-looking infrared. There are a number of different tools and technologies out there. IR imaging is used for all sorts of stuff. They use it to look for, like in factories, they'll use it to look for heat sources, right? The military obviously used FLIR for some of the Tic Tac videos. And I think I have a couple of images of those. You're going to get heat signatures there, absorption or emission of heat, right? So earlier we were talking about the Searle effect generator. Supposedly that device runs cold. If that's the case, it's going to show up in a different color with your infrared imaging than it does with standard imaging. That can help tell us what's going on. Is this thing emitting energy or absorbing it from the surrounding environment? That would be very interesting. It could tell us more about what's going on there, as well as if we use calibrated equipment. Again, this exists for infrared. It could tell us what the temperature is, and it could help detect stuff like air friction. So these are existing photos. The two on the left are from the Nimitz incident. The two on the right are more recent. Um, so these are existing examples of infrared photography of UAP. Okay, so then ultraviolet, I have been searching. I was not able to find any UV images for UAP. There are lots of them out there. They use this for a number of different things. Again, it's a different spectrum. Instead of being lower than visible light in terms of energy, it's higher than visible light in terms of energy. A lot of insects use some UV imaging. Another interesting thing is most camera equipment, including your smartphone camera, can see a little bit into the UV spectrum. They actually use filters on those to prevent that from happening. And there are companies out there that produce basically filter removed cameras. They'll take them off the lens, they'll take them off the sensor. I believe you have to use somewhat different lenses. If I remember right, you have to use quartz instead of glass. That works better. And you can see near field UV with just regular cameras, right? And so then your megapixels are going to continue improving. The cameras that I've seen out there are more of the 12 megapixel size. They're trailing the commercial market, but hey, it's getting better. They are used already for a number of different things. One of the big ones is sunscreens, believe it or not. They'll do photos to see how well sunscreens work because the sunscreen will be absolutely clear in the optical spectrum. You put it on and it will be completely white, right, as it reflects the UV in that spectrum. There are also specialized cameras that can see a lot deeper into the UV spectrum. Faraday rings. So this is their very high intensity magnetic fields. Jared was talking about this a moment ago. Ray Stanford took photos he believed show Faraday rings. Jared Yates and Charles Crawford dug in there. These are concentric circles of distortion in optical images. So these are the images that Jared showed me. He sent these over. These are somewhat enhanced to show the Faraday rings, but the general idea is you're going to see these ripples because it delays. Basically, you get an effect where it delays part of the light traveling. So I'm not going to get too deep into that, but this is something where very, very high intensity magnetic fields may create these. Gravitational lensing. This one is really exciting for me because the Aguadilla UAP appeared to split in two and come back together, and there appeared to be what's called shape shifting. Shape shifting is something that is very common in UAP reports, and no one has a good explanation for it. Well, Chad Wanless believes that optical distortions in UFO photos and video could indicate gravitational lensing, which is just light being bent in a strong gravitational field. And so this could be used and measured to understand or map drive systems. It may include red or blue shifting, mirage effects, objects simply disappearing, reappearing later, potentially splitting in two, as well as just all sorts of different shape shifting behavior. The craft itself may not change at all in shape, but the light that is coming out of it, the light that's bouncing off it that reaches your eye, is being bent by this field. And if the craft is using some kind of a warp field, as it travels, especially when it turns, that field is going to be changing. It may change the way the light reflects. So the downside to trying to map these is we may mistakenly identify them based on JPEG compression, right? Because you get those little pixels around the image, MP4 compression, which is the same thing in video, as well as normal photographic distortions, especially in your older photos. Those cameras weren't that sensitive, so they had to keep the lens, they had to keep the iris open longer, right? So you hit the shutter, it opens up, light comes in. If something is moving, you could get some blur. That's not from gravitational lensing. That's just normal blur. So these are a few of the images that Chad Wanless has shared, and he actually just published a book about this. I would suggest if anybody is interested, look up his name, Chad Wanless. He is with MUFON, and he just finished working with a PhD electrical engineer to try and map these out. These are just a few of the images that he had. And again, you could see these series of white dots are what he believes to be distortions from gravitational lensing. Okay, so another one, this is going back to UAPX, and I need to make this slide a little more clear, is Geiger counter, cosmic watch. I believe scintillator is another thing. There are several different tools that are used to measure radiation, right? They use them in nuclear plants, all sorts of stuff. It would be interesting to be able to pick up readings from those. My thought is for something like that, it's probably going to be super short range. But UFOs have been associated with residual radioactivity at purported landing sites. There have been reports of personnel in the vicinity of UFOs, people who stand too close or it flies over their head, getting symptoms that look a lot like radiation exposure. And then there's also a tremendous history of correlation between UFOs and nuclear materials, storage, processing, vehicles, weapons, you name it. So it would be interesting to see if we can pick up data on that. Maybe nothing comes out, but maybe something does. Portable neutrino detector. This is very, very new, very hypothetical. I actually have a story on this. A university just developed this a couple of years ago. They are doing things a little bit differently. As you may know, traditional neutrino detectors, you have like this massive cavern full of light detectors. And you fill the thing with water, right? Like in Antarctica, and you just wait, and maybe like a year or two goes by and you see a flash of light, and that's your neutrino. This thing apparently it's tabletop, right? So you could it's portable and it is a little bit more sensitive in a different way. So maybe that's something. The reason I wanted to mention this was this UAP nuclear correlation. I've wondered if it could be related to the fact that neutrinos really aren't shielded by traditional nuclear shielding. So, in other words, your aircraft carrier has a nuclear power plant. Okay, so maybe the radiation is very, very well shielded by the craft, by the way that they built it, by the tons and tons of metal that surround it. Those neutrinos are going to go right through it. So if UAP are seeing neutrinos, it's going to look like a light bulb, which could be why they are attracted to those. So if that's the case, maybe we should be checking them for neutrinos as well. Then the last couple here, because I think I've only got a couple slides left. Oops. Audio detection. This is kind of a no-brainer, right? Some UFOs have been reported with a humming sound. Some people have reported other sounds. So the question becomes, okay, can we do audio detection? Maybe we can record a sound. Again, by itself, not very useful. But if you're able to get video and you get audio with it, who knows? Another thing that we might be able to detect there is smaller sounds, right? Lesser sounds from things like air friction, air pressure. If you hear a whooshing noise, that may show some interaction with the environment. We could use that to help provide more data. And then another aspect to this is an atmospheric sonar system like Tesla's used to use for imaging, right? Most cars still have backup alarms that are similar to this, where basically it just sends out a sonar ping like a bat, just like radar, except that it's sound and it listens for the response and it can tell you how close things are and provide some imaging. The upside to something like this is it gives you another mode for imaging that's completely unrelated to others. So maybe you've got interference with optical, you could pick it up with audio. The downside is obviously these are going to be very, very short range. So there's audio and then there's sonar. And I didn't want to leave this out. Basically, this is just audio imaging in the water, right? And the reason I wanted to put this in was it has reportedly detected several UAP, USO in historical naval encounters, right? And the details for this have not been as forthcoming as I think we've all hoped, but there have been several rumors of very big encounters where you get sonar detection of, I believe, what they call fast movers underwater, right? And so that is all basically underwater audio. It can help identify distance, speed, and size for submerged UAP. And depending on, and again, I'm not a sonar expert, maybe you could listen for sub sounds also to tell, maybe it's giving off, I don't know, some other noise. I did have a couple of general considerations. Optical imaging is getting better and better and better. Um, as it gets better, we're going to see higher quality UAP video emerge. I think that's something that is easy to forget, right? But you look back to the beginning of UFOs and you get this grainy, blurry image, and somebody says, "Oh, look, it's an alien spacecraft." Okay, well, who can tell, right? It's a bright, overexposed light on a dark background. Okay, then you fast forward to stuff like the 2004 Nimitz, where it's still difficult to tell, but you can kind of see an outline. You can see the outline of it traveling. You can say, okay, there's more detail here. Well, by today's standards, those are incredibly outdated images. So as these things improve, the imaging that we have is going to get better and better and better. I think one thing that probably won't get better as well is the fact that these are at a distance. And if you're taking smartphone images with them, you're always going to have problems with zoom, right? And so that is something where like people take their smartphone out and they try and get an image of the moon. And it's the same thing. It looks big to you, you get it on camera and it's tiny. So there are some physics limitations there, other limitations with sensor quality because they're small sensors in these phones. But the fact that everyone has a recording device in their pocket and the fact that the megapixels and the color palettes are getting so much bigger so fast, that is a giant boon. Again, newer file systems provide more colors, fewer artifacts from image compression, and radar and other technologies, infrared, for instance, those are also moving forward at a rapid pace. So that is my walkthrough on multimodal imaging.